This is maybe my favorite day of the whole semester when we prove that the two different definitions of continuity are actually equivalent. If you've been watching our series, you know that we've defined continuity in terms of sequences, but also with the epsilon delta definition. And we do both because sometimes one is more convenient and sometimes the other is more convenient. But we have to show that they're the same. And this isn't one of the deepest results of the class, but it's definitely a non-obvious fact. And when going through the proof, you actually find something really beautiful and creative about math and about logic. And I think that's why it's so close to my heart. Now, the proof is kind of technical. We won't go through all the details, but I want to explain what happens when you try and go through the proof yourself. So first of all, let me just say, if you go from property 2 to property 1, right, assuming property 2 is true, then it's not so hard to show that property 1 holds as well if you just work out what you're given. And maybe put your thoughts in the comments if you want to try and type your own proof. I'd love to give you some feedback. The more interesting direction is when we say that starting with property 1, how do we know that property 2 is true? And this is really a serious question because you're given a lot of information, right? You're given that no matter which sequence of points you have, as long as they're converging to some point A, then their outputs, after you plug them into a function, have to converge to that point f of A. That seems like a ton of information that you have, but here you're being asked to show something about all inputs x within some range or some neighborhood of that point A. And that difference is kind of huge because no one sequence, or actually any countable number of sequences, could possibly capture information about the uncountably many points that are going to be in this delta neighborhood of A. Let me rephrase this. If we tried really, really, really hard to write a direct proof of what's going on, we would get stuck. And we would get stuck and we would maybe scratch our heads and try to figure out what we could do. I mean, after all, we have information about sequences, but there's no sequence kind of like staring us in the face. Or is there? And so if we change our mindset just a little bit and we say, you know, maybe this isn't true. What if we tried to argue by contradiction and see where that gets us? And here's how that would go. So let's fix some epsilon. And now imagine that delta equals 1 was not small enough, right? That didn't work for this property. Okay, well, delta equals 1/2. Well, let's say that didn't work either. And what about delta equals 1/3? Well, that doesn't work either. And in fact, let's go through and say that delta equals 1 over n never works, no matter what n is. That sounds like a sequence of deltas that do not work. Well, what does it mean if a delta doesn't work? Well, it must mean there's some input that's within that tolerance delta of A, such that the outputs are not going to be close to the value they're supposed to be close to. Oh my gosh, it sounds like we just created from our sequence of deltas a sequence of inputs. And now we can go ahead and use property 1. Obviously, lots of details to go into there, but I love this proof because one direction, going up, is pretty straightforward. Nothing out of the ordinary there, just using what you have. But in the step going down from 1 to 2, we really do need that proof by contradiction. At least that's the simplest proof that I know. And I just think that's kind of cool.